and third component here is both are finite, then you will get reaction torque. Reaction torque is mainly because of mutual flux. Reluctance torque is mainly because of self flux. Right? Keep in your mind. Try to remember this expression. This expression later we'll try to understand based on the structure of the machine. Right? If machine is cylindrical machine, this first component, third components are 0. Only second and fourth components will enter in the picture. If machine is salient pole machine, right? So, right? Then these 4 components are enter in the picture. If machine is there is no winding on the rotor side, only no winding. If it takes switch reluctance motor, only first component and third components are entering the picture. Anyway, in here in case of switch reluctance motor, there is no IR. That's why third component is also 0. Only first component is entering the picture in switch reluctance motor. So these are all the structures of the surface mounted interior permanent magnet synchronous machine, induction machine. Figure A is belong to surface mounted permanent magnet synchronous machine. Figure B is interior permanent magnet synchronous machine. Figure C is induction machine. Figure D is synchronous reluctance machine. Figure E is permanent magnet synchronous reluctance machine. Figure F is switch reluctance motor. Here one more important thing is, if you take A, B, C, D, E figures, up to E figure, stator construction is similar. Even if you take surface mounted permanent magnet synchronous machine, interior permanent magnet induction machines, synchronous reluctance machine, right? Permanent magnet synchronous reluctance machine, stator construction is similar. Stator winding is distributed type. It is not a concentric winding. Next, come to switch reluctance machine. Stator poles and rotor poles both are projected type. At the same time, winding, it is not a distributed type. It is a concentric type winding. So what are the advantages? If winding is distributed, then what is the advantage of the electrical drives? If winding is distributed, the main advantage is air gap flux. Air gap MMF becomes sinusoidal. If air gap MMF is sinusoidal, automatically you will get unidirectional torque. Right? Come to SRM. In case of switch reluctance machine, here torque is discontinuous mode. Why torque is discontinuous mode? In next slide, I will try to explain why torque ripples are more in SRM. Here, what are the drawbacks of SRM in electric vehicles in braking mode? We'll try to discuss. Right? So, in case of surface mounted permanent magnets, here this is called rotor core. There is no winding on the rotor side. This red one and green one are permanent magnets. Alternating poles are placed on the rotor surface. That's why it is called surface mounted permanent magnet. Come to interior permanent magnet. Here permanent magnets, alternate permanent magnets are placed inside the rotor core. That's why it is called interior permanent magnet synchronous motor. Right? This is called induction machine. Here copper bars are placed on the rotor surface. Right? Rotor teeth is also there. Because rotor teeth, you will get teeth harmonics. Right? This one. This is called synchronous reluctance machine rotor structure. No winding on the rotor side, but air gap is non-uniform. Because of this non-uniform air gap, reluctance torque is entering the picture. Come to here. Permanent magnets are placed in the rotor side. No winding on the rotor side. That's this machine is coming under permanent magnet synchronous reluctance machine. This machine. Surface, this is switch reluctance machine. No winding on the rotor side. Rotor poles and stator poles both are projector type salient structure. That's why there is no reaction torque. Only reluctance torque is there in switch reluctance motor. Come to special machine characteristics. These are all the characteristics of special machine. Performance wise, torque, power density, efficiency of the special machines are more compared to other machines. Why efficiency is more? Reason is no rotor copper losses, mechanical stress is very less, mechanical vibration, mechanical losses are less, electrical losses also less, automatically efficiency of the drive will improve. The main drawback of special machine is cost. Second point, machine cost compared to conventional machine. These machines are expensive. Why? Because it required converters also, position sensor is also required, encoders, tacho generators are required. Taco generator no one is using generally. Why taco by using taco generator we can sense the speed, right, but we cannot sense the position. That is the problem with taco generators. That's why encoders are required. By using encoders we can sense the rotor pole position. One more advantage of the special machine is reliability, fault tolerance. Here, so here each special electrical machine, uh, characteristic, advantages, drawbacks. By using next slide we'll try to understanding special machines application: electric vehicle, aerospace, wind generators. Why aerospace also? Why special machines are day-to-day applications in electric vehicle, aerospace, wind generators are increasing? Reason: the main advantage of these special machines are size of the machine is very compact, right, very less. Weight is also very less, size also very less compared to other machines. Other conventional machines are very bulky, especially in aerospace, wind generators, electric vehicles. Size is main constraint, right? So here that's why the applications of the special machines are increasing in electric vehicle, aerospace, wind generators. Wherever space constraint is there, you can select special electrical drives. So by using this, this is the comparison according to their capability of the each drive, right? So color, try to identify the colors. Surface mounted permanent magnet synchronous motor, color is blue one. Interior permanent magnet character blue, this violet. Induction machine green. Synchronous reluctance this yellow. Next, this is ferrite type, ferrite material. Next, permanent magnet synchronous reluctance machine SRM, right? Switch reluctance motor is red color. What is the advantage of switch reluctance machine? Compared to all other machine, the main advantage of switch reluctance machine is DC link utilization. This is the peak point. This is the peak point here of the SRM. DC voltage utilization is more in case of SRM. Next, one more advantage of this SRM is fault tolerance is also more. Why fault tolerance is more? Especially in electrical drives application, even one of the phase is getting fault, machine should be operated in continuous mode, right? In case of SRM, generally stator winding is concentric type winding. It is not a distributed. If there is any fault in the one coil, you can replace. You no need to replace immediately. Without one coil also, we can continuously operate we can operate the SRM. If you take distributed winding, if there is any problem in the one coil, immediately you need to stop the drive and you need to replace the machine, right? That's why fault tolerance of the SRM is more, because of advantages concentric winding. Here you need to take concentric winding on stator side. So concentric winding advantages, even one of the coil getting fault are getting open. By using other coils also we can get continuity. We can continue operate the drive. Next, come to surface mounted. The advantage of the surface mounted is torque ripples are less. This is the main feature of surface mounted permanent magnet synchronous machine. Why torque ripples are less, later I will try to explain, right? Next, one more advantage is power factor of the machine is very good. Surface mounted permanent magnet synchronous machine power factor is very good. Interior permanent magnet synchronous machine power factor is also very good. Interior permanent magnet advantages, efficiency is more. Torque per power density is also more for interior permanent magnet synchronous machine, right? Come to induction machine. Induction machine main advantages, noise and vibrations are very less, right? This is the peak point of the green compared to here other drives. Induction machine peak point is reached to this characteristic, noise and vibrations, right? Next, synchronous reluctance machine main advantages here, field weakening zone. Even SRM also main feature is field weakening zone. So by using this diagram, you can understand. So what are the uh, different, what are the special features of the SRM? Special features of the SRM is here compared to other machines, DC utilization is less. Field weakening is also, characteristics are very good. In field weakening zone, we can operate SRM. Next, fault tolerance also very good for SRM. Come to surface mounted interior permanent magnet. These two are permanent magnet synchronous machine. The advantage of permanent magnet synchronous machines are, compared to all other machine, advantages are power factor is very good, efficiency is also very good, torque ripples also very good, very less compared to other machines. Next, torque per power density is also more for permanent magnet synchronous machine, right? These are all the different nature characteristics of the machine, right? So come to statistics. So by using this diagram, we can understand here what are the applications of special electric motors characteristics, especially in electric vehicles. Here, special electric motors, 42% they are using special motor. 42% motors are electric motors, special electric motors. Next, electric motors uh, they are using in wind applications, 14%. 11% in aerospatial they are using special electric motors. Next, robotic application, 3% special machines they are using. Next, domestic tools application, 3%. Other applications they are using 27%, right? So these are all the statistics of the special electric motors in different applications. So what are the conclusions, final conclusions from this slide? Almost 42% applications, 42% special electric motors they're using in electric vehicles, right? After that, wind turbines, especially in wind turbine, earlier days they were using slip ring induction machines, right? So nowadays, slip ring induction motors they are trying to replace with permanent magnet synchronous drives. The advantage of the permanent magnet synchronous machine is you no need to supply the reactive component. Here, the main drawback of slip ring induction machine is whenever machine is operated in generating mode, here even machine is operating in generating mode, throughout the operation you need to supply reactive power, right? You need to excite the stator poles. In order to excite the stator poles, you need to supply reactive power. In order to supply the reactive power, it required capacitor banks, extra capacitor, additional cost it will increases. That is the drawback of the slip ring induction machine. If you take permanent magnets on the rotor pole, here by here by using wind you can get mechanical force, right? You don't need to supply any reactive power to the wind drives if you take permanent magnet synchronous machine. That's why here nowadays most of the slip ring induction drives are replaced with permanent magnet synchronous motor drives, special machines. So come to electric vehicles statistics application wise. Here's here 67 motors are motors in electric vehicles are SRM, right? 8% permanent magnet synchronous machine, 25% induction machine. Nowadays, here in most of the cases, most of the electrical drives, they are trying to replace SRM induction machine with permanent magnet synchronous machine. Here, still there is a lot of research is going on permanent magnet synchronous machine. The main drawback of permanent magnet synchronous machine, it is very expensive compared to other special machines, other conventional machines. Here, the permanent magnet material cost is very high, very expensive compared to other machine. That's why still it is under research on here. The applications of the PMSM is only 8 to 10%. In future, you can expect permanent magnet synchronous motor electric vehicle applications. It will go more than 70 to 80%. Here, compared to all other machines, permanent magnet synchronous machine having special characteristics. Main characteristic, power factor is very good. Power factor, if power factor is good, advantages machine will take less current. That is the main advantage of PMSM drive. One more advantage is torque per power density is more, efficiency is also very good, right? These are all the features. Size is also very compact. One more advantage of the PMSM is torque ripples are very less compared to switch reluctance motor compared to induction machine, right? So this is the diagram for switch reluctance machine. So stator poles are projected type, rotor poles also salient type, right? No winding on the rotor side. Concentric winding is placed on the stator side. It is stator winding is not yet distributed. So if you take concentric winding, arrangement is very easy. Replacement of the winding under damage condition is also very simple, very economical also. The advantage of switch reluctance machine with respect to construction point of view, no permanent magnets on rotor side. It is only ferromagnetic material. Ferromagnetic material you have to take on rotor side. Compared to permanent magnet, ferromagnetic material cost is very less, right? Under fault condition also, here replacement of the winding is also very simple, right? So by using this characteristic, so this is the characteristics of switch reluctance motor. By using these characteristics, we can understand what are the main drawbacks of switch reluctance motor in electric vehicle in regenerative braking. We can easily understand why torque ripples are more. Also we can easily understand by using this characteristics, right? Come to, so in case of switch reluctance motor, the generated torque is directly proportional to, this is the mathematical expression for reluctance torque generated by the switch reluctance motor. If you take this expression, torque is directly proportional to I square into dl by d theta. If there is any change in the inductance is there, immediately torque is enter in the picture. So here, come to diagram. Let us assume that here stator poles are stationary, rotor poles are moving from left to right, right? So before understanding the characteristics, first you have to assume that the stator poles are stationary, rotor poles are moving from left to right. Initially, let us assume that rotor poles are, this is diagram 1, diagram 2, 3, 4. Let us assume that initially rotor poles are far from the stator. Once rotor poles are moving towards stator pole, what is happening? Flux linkage, stator pole flux linkage is increases. If flux linkage is increases, automatically inductance offered by the inductance of the stator winding with respect to rotor pole is also increases, right? So if rotor poles are far from the stator poles, what is happening? Reluctance offered by the rotor pole with respect to stator winding is more. If reluctance is more, flux linkage is less. If flux linkage is less, automatically inductance is also very less. Stator winding inductance becomes minimum. This is the position of minimum inductance if rotor pole is far from the stator pole. Once rotor pole is moving towards, once rotor pole is moving towards stator pole, what is happening? Flux linkage is increases. If flux linkage is increases, automatically theta is also here. Sorry, automatically inductance is also increases. Once rotor pole is aligned with stator pole, what is happening? That is the minimum reluctance portion. If reluctance is minimum, what is happening? Inductance becomes maximum. If inductance is maximum, further there is no change in the inductance. Inductance becomes constant. Next, after completion of this cycle, take one more assumption. Take one more cycle. Once this pole is moving away from the stator pole, what is happening? Again, flux linkage is coming down. Inductance, flux linkage is decreases. Inductance is also decreases. So by using this diagram, this characteristic, we can understand why what are the precautions we need to take switch reluctance motor in electric vehicles when our machine is operating in the generating mode, when our machine is operating in motoring mode? What are the precautions we need to take? What are the drawbacks of SRM? We can easily understand by taking this simple diagram, right? So because of salient structure in the stator core and rotor core, stator winding inductance with respect to rotor pole is always like this, like trapezoidal, right? So for understanding purpose, take this zone theta naught to theta c. In this zone, inductance is variable. So whenever rotor poles are enter in this zone, in the zone, immediately you need to excite the stator winding. If you supply current here at the same in this zone, when our rotor poles are enter in this zone, you need to supply the current, you need to excite the stator pole. Once stator poles are excited, automatically torque becomes finite. Torque is inductance dl by d theta is constant in this zone. Same time dl by theta is constant. Same time current is also finite. Then you will get positive torque. Right? When our rotor poles are enter in the zone, immediately you have to unexcite the stator poles in motoring mode. Otherwise, what is happening in motoring mode, positive torque is required. If you want to generate the positive torque, here you need to excite the stator poles when our rotor poles are lies in this zone. Otherwise, when our rotor poles are lies in this zone, you should not excite the stator pole. Otherwise, you will get negative torque. Negative torque, because of this negative torque, here this negative torque is always working opposite to the positive torque. Because of positive torque, let us assume that rotor is twisting in clockwise direction. Automatically, because of negative torque, rotor will move in anti-clockwise direction. Finally, rotor will vibrate for one off cycle, right? For one complete. So, when our machine is operating in the motoring mode, this component is required. This is unwanted component, right? That's why you need to unexcite the poles. When we need to excite the poles, when our rotor poles are, so let us assume that if you want to operate the SRM in motoring mode, right? Motoring mode. So here this positive torque is required. When our machine is operating in generating mode, this torque is required. Next, one more thing is when our rotor poles are moving towards stator pole, you need to excite the stator winding. Then automatically you will get positive torque. When our rotor poles are moving away from the stator pole, you need to excite the stator. You need to excite the stator winding. Then you will get negative torque. Negative torque is nothing but you will get your machine is operating in generating mode, right? So here in case of SRM, problem is here there is no continuity of the torque. Here dl by theta in this zone is 0. That's why torque amplitude is 0. Next, in negative portion also you need to unexcite the winding. Then this component is also 0. So there is lot of there is no continuity in the torque. That's why if torque is discontinuous, because of this discontinuous torque, you will get vibrations, right? This is called ripple component. Generated torque should be always continuous and unidirection. But in case of switch reluctance motor, because of salient structure of the stator pole and rotor pole, here reluctance torque is entering the picture. The nature of the reluctance torque is always you will get positive torque and negative torque based on the position of the rotor pole. You need to by taking position sensor, you need to identify the rotor pole position. By identify the rotor pole position, here we can decide whether stator poles are excited or stator poles are unexcited. Based on the mode of operation, we can decide, right? If machine is operating in motoring mode, uh, you have to excite the poles when our rotor poles are moving towards stator pole. If you want to operate the machine in generating mode, when our rotor poles are moving away from the stator poles, you need to excite the rotor poles, right? So by using these characteristics, here we can conclude that torque is there is unwanted torque component is entering the picture. Because of this reason, you need to unexcite the poles when our rotor poles are moving away from the stator poles in motoring mode, right? So here let us assume that this torque is 0. Current is in this zone, current is 0. Automatically this component is 0. Then you will get from here to here, from this point to this point, there is no torque component, nothing but torque is in discontinuous mode. This is main drawback of switch reluctance motor. Because of this discontinuity of the generated torque, here what is the drawback? Discontinuity of the generated torque, you will get ripple component, right? If torque is uniform, then rotor it will rotate in very smoothly. Because of this discontinuous of the operation in the torque, ripples are more in SR. So come to advantages. The main advantage of the switch reluctance motor is it is very less cost. Production cost is very less. Efficiency compared to other machines, efficiency is more. Why? Because no losses, rotor copper losses on the rotor side. Next, torque speed characteristics also very good. One more advantage of the SRM is rotor is smallest of any machine, lightweight. If weight of the rotor is very less, inertia is less, then advantage is acceleration uh, rate is very fast. Here, if acceleration time is very less, advantage is we can save lot of energy in accelerating mode. Please try to understand. If you take any electrical drive, here there is a lot of energy is wasted in terms of heat during accelerating period or deaccelerating period. If acceleration time is more, heat dissipation time is more, machine will get damaged. Insulation, it will lose their property in this period. You have to take care about insulation also. Okay, that's why if acceleration time is less, then advantages we can save a lot of electrical energy. We can reduce the heat dissipation from the winding. So one more feature of switch reluctance motor is machine does not produce any cogging and crawling torque. Here, if you take induction machine or PMSM drives or BLDC also, here these machines are suffering due to this crawling and cogging and crawling tasks. These two are unwanted components. Here these two unwanted components are you no need to worry about these two unwanted components in switch reluctance motor. Switch reluctance machine, it will not produce any cogging tasks, right? Come to BLDC machine. So in case of BLDC machine, here rotor core is cylindrical type one. Permanent magnets are placed on the rotor core surface, but stator poles are projected type. Stator winding is also concentric winding, right? So if here now what is the basic? Many of the scholars, many of the researchers here still they are getting doubts. Why PMSM machine applications are more in electric vehicles compared to BLDC machine, right? Why BLDC motor is applicable for only low power drives? Why PMSM drive is applicable for medium and high power application? More than 50 kilowatts also we can go PMSM. Why above 10 kilowatts power application BLDC no one will prefer? By using this concept, by using these waveforms and by using this slide, we can easily we can conclude, right? Come to PMSM drive. In case of PMSM drive, stator winding is distributed type, right? Because of distribution nature in the stator winding, here you will get this blue one is counter EMF. The nature of counter EMF induced generated in PMSM drive is sinusoidal because of distribution winding. If counter EMF is sinusoidal, by using power electronic also we by using different PWM technique, we'll try to generate um, resultant voltage closely to sinusoidal. If applied voltage is sinusoidal, counter EMF is sinusoidal, automatically current is always depends on potential difference between applied voltage and counter EMF. Counter EMF is sinusoidal, applied voltage is sinusoidal, automatically resultant current drawn by the PMSM is also sinusoidal. But in case of BLDC machine, stator poles are projected type. Stator winding is concentric winding. Because of concentric winding nature, here the nature of air gap MMF is always looking like trapezoidal. If air gap MMF is trapezoidal, automatically counter EMF is also trapezoidal. Here, if applied voltage is sinusoidal, counter EMF is non-sinusoidal, then machine will take non-sinusoidal current. So what are the conclusions? BLDC machine, it will not take sinusoidal current. It will take non-sinusoidal current. Non-sinusoidal current nothing but there are the resultant current having other high frequency current components. Because of this high frequency other high frequency current components, other communication signal electronic circuits will get damaged, right? That's why BLDC machine generally for low power application you can prefer. For high power applications, non-sinusoidal current with high magnitudes, here other circuits, other electronic circuits will get damaged. Heat dissipation is also more in BLDC machine compared to PMSM drive. So that's why in electric vehicle application, generally electric drives application, they will select PMSM. BLDC only for low power application. These are all the applications of BLDC motors, generally for machine tools application, aerospace application, electric bicycle application. Here medical companies, robotic application. Next, wind generators. In case of wind generators, there are two types of special machines they are using. One is permanent magnet synchronous motor, another one is BLDC machine. Permanent magnet purpose is to generate the power. BLDC motor purpose is to change the position of the wings based on the wind direction, right? BLDC motor they are using for auxiliary motor. PMSM drive they are using for main motor, generating power. To generate the power, PMSM drive motor they are using here for changing the position of wings. These are all the typical applications of BLDC motors. Computer hard drives, DVD, CD players, electric vehicle, low power electric bicycles, industrial robotic, washing machine, compressors, dryers, fan, pumps, and blower application they're using. For BLDC less than 10 kilowatt application, you can go for BLDC machine, right? Next, why PMSM? Why PMSM mission day-to-day applications of the PMSM mission in domestic application, industrial application, electric vehicle application, aerospace application? Why this mission become here very powerful compared to other special missions, right? So the main feature of the PMSM mission, high torque inertia ratio, power density is also more. If power density is more, automatically here dynamic response is also it will improve. Next, power factor is also very good. Why power factor is very good for PMSM? Here you no need to supply when our machine is operating under no load condition. Here uh, uh, you no need to, under no load condition, machine will not take any reactive component. Stator side reactive current component is not required for PMSM drive under no load condition. This is the main advantage. Here, if operating power factor of the PMSM under no load condition is very good, automatically under load condition is also very good compared to other machine. Take example induction machine. In case of induction machine, when our machine is operating in no load condition, it will take 25 to 30% of the magnetizing current. Here, power factor of the induction machine under no load condition is very poor compared to other machines. That's why here by taking PMSM we can improve the power factor. No load condition is very good, automatically load condition automatically it will improve. Efficiency of the PMSM is also more. Reason is no winding on the rotor side, no copper losses, mechanical no teeth on the rotor side, no mechanical stress also, mechanical losses also less, automatically resultant efficiency it will improve. The main features, another special feature is very compact, size is very less, excellent dynamic property, high performance operation. These are all the features of PMSM. That's why because of these features, day to day the applications of PMSM it is increasing in practical condition. So here this is for induction machine construction, PMSM construction. Stator construction of PMSM induction machine, both are similar, both are same. But rotor construction, there is no winding on the rotor side, only permanent magnets are placed on the rotor. Rotor core is very smooth, there is no rotor teeth, right? Come to stator induction machine side, rotor teeth are there. Because of this rotor teeth, you will get rotor teeth harmonics, right? That we cannot, very difficult to eliminate space harmonics. Time harmonics we can control, but space harmonics are mainly here because of this mechanical structure, it will enter in the picture. These are all the applications of PMSM, electric and hybrid electric vehicles you can select. Next, machine tools also, servo drives, industrial drives, pumping, centrifugal renewable energy systems like wind turbines you can use. Domestic applications like washing machine, vacuum cleaners also you can use. So this is the comparison between induction machine and PMSM. Efficiency of the PMSM is more, power factor is very good, dynamic response is very fast, Operating speed is also more. Overload capability also more for PMSM machine. Torque triples are more in case of induction machine. PMSM torque, the resultant generator torque is very smooth, right? Come to PMSM drive. Basically, PMSM's drives are classified into two parts based on the arrangement of the permanent magnets on the rotor side. So this figure 1 is coming under surface mounted permanent magnet. Permanent magnets are placed on the rotor surface. That's why figure 1 is belongs to surface. It is called surface mounted permanent magnet synchronous machine. Figure 2 is permanent magnets are placed inside the rotor core. That's why it is called interior permanent magnet synchronous machine. So by using this diagram, we can understand why surface mounted permanent magnet synchronous machines are very powerful than interior. Here we can easily understand. Come to here. Now here, if you take permanent magnet characteristics, the nature of permanent magnet is the the permeability of the permanent magnet is exactly equal to air permeability. Air permeability and permanent magnet permeability here both are same, both are having same values, right? So here once again I will try to repeat. Please try to understand. Permanent magnet permeability, air permeability having both range, both value, both are same. Air permeability and permanent magnet permeability are both are same only. Then here come to here. So take this point as a reference. With respect to this point, we'll try to take to here. If you take this figure, take this is the reference point. With respect to this reference point, draw two lines. One is in phase with pole axis, another one is interpole axis. This is the interpole axis, this is the pole axis. Okay. So with respect to pole axis and with respect to interpole axis, the reluctance offered by the air gap is same only, right? Interpole axis air gap reluctance, interpole this axis and this axis uh, reluctance is same. So here if a pole axis reluctance and interpole axis reluctance both are same, then what is happening with respect to air gap flux, uh, in this axis and in this axis reluctance is same, then flux distribution air gap is uniform. Air gap is uniform, nothing but here if air gap is uniform, then there is no reluctance torque. In case of surface mounted permanent magnet synchronous machine, there is no reluctance torque. You will get only reaction torque, right? Why there is no reluctance torque? Reason is air permeability and permanent magnet permeability both are same. Here with respect to this point, interpole axis reluctance and pole axis reluctance both are same. So there is no non-uniform air gap. Air gap distribution is uniform with respect to magnetizing flux, then automatically there is no reluctance torque. Come to here, interpole. Take here, this is the core is there, ferromagnetic material is there. With respect to this point, take pole axis. The permeability of the permanent magnet is equal to air. Here compared to iron, permeability air permeability is very less. Iron permeability is more. Reluctance is very less. With respect to this point, here uh, magnetic axis reluctance is more. Interpole, this is called interpole axis. Interpole axis reluctance is less. Nothing but what are the conclusions here? Here in figure 1, magnetic axis and interpole axis reluctance are same, but here magnetic axis reluctance is more, here reluctance is less. That's why with respect to magnetic flux, air gap reluctance is non-uniform. If air gap reluctance is non-uniform, automatically reluctance torque is entering the picture. This is called one more expression, torque expression in terms of LD LQ, right? In case of LD is nothing but reluctance, inductance with respect to magnetic axis. LQ is nothing but quadrature axis or interpole axis. In case of surface mounted, LD and LQ both are same. That's why second component is 0. Nothing but reluctance torque is 0. Only reaction torque is there. But in case of interior permanent magnet, reluctance torque is enter in the picture. LD and LQ is both are not same. LD is nothing but with respect to magnetic axis. LD is reluctance is more, LD is less. With respect to interpole, LQ is more. That's why LQ is more than LQ is more than LD. So in case of interior permanent magnet, reluctance torque and reaction torque both are entering the picture. Next, one more advantage of the surface mounted permanent magnet synchronous machine is these permanent magnets are closely to stator winding. If permanent magnets are closely to stator winding, here leakage flux amplitude it will coming down. If leakage flux amplitude is decreases, automatically mutual flux strength it will increases. Once mutual flux amplitude is increases, automatically energy transfer from rotor to stator it will increases. Energy conversion rate is also increases here because of less leakage flux. But in case of interior permanent magnet synchronous machine, permanent magnets are placed far from the stator winding. If permanent magnets are placed far from the stator winding, automatically here leakage flux increases. Leakage flux amplitude is increases. If leakage flux is increases, energy transfer from rotor to stator it will coming down. Right, that's why in most of the cases they will prefer surface mounted permanent magnets. The applications of the interior permanent magnets also more. Why? Because rotor here physically, um, mechanically this rotor core is looking like cylindrical, but surface mounted it is looking like salient. But with respect to magnetic flux, this rotor structure, salient structure, magnetic flux it will treated as a cylindrical machine. But in case of interior permanent magnet, with respect to magnetic flux linkage, this rotor cylindrical structure it is treated as a salient structure. With respect to mechanically interior permanent magnet is looking like cylindrical, but basically with respect to magnetic circuit it is a non-salient structure. Right, these are all the classification difference between interior permanent magnet cylindrical machine and surface mounted. Surface mounted problem is here air gap is with mechanically centrifugal forces acting on permanent magnets are more. Here rotor surface is more, but here mechanical stress is less. Right, come to electrical machines and drives in hybrid vehicles, induction machine, permanent magnet synchronous machine, brushless DC machine, SRM. This machine generally they are using for electric vehicles and hybrid electric vehicles. So come to now, till now we have a concentration on fundamentals of the only machine side. Right, so there are so many machines are available. AC machines are available, conventional machines, again special machines. Here what are the advantage of special machines compared to conventional machines? Already we discussed the main advantage of special machine is no winding on the rotor side. If mechanical losses and electrical losses are less, stress on the rotor core is also very less, size is also very compact compared to conventional machine. Based on this based on these features, we can easily conclude that special machines you can select for electrical drives applications nowadays. Right, come to now we'll try to put concentration on control side. Now mission characteristics over. Based on the mission characteristics we can select the motor. Next, after selecting the motor, how to control part is also important. Right, come to control side. Now we'll try to put more concentration on the control side. After that we'll try to discuss application. Last part is application. This total presentation I classified into three parts. One is mission part, another one is control part, last part is application. Later, after completion of the control part, we'll try to discuss application part. Right, now this is the basic diagram. block diagram for any electrical drive. If you take AC drives, DC drives, or special electric drives also, this block diagram is common, right? There are 1, 2, 3, 4, 5, 6 blocks are there. Out of these 6 blocks, as a electrical scholar, you need to give more priority to the load, right? Our main objective is we need to satisfy the load. In order to satisfy the load, first step is here. In order to meet the load requirement, step 1 is first you should know the load characteristics. So if you have if you know the load characteristics, if you know the requirement of the load here, so based on the load characteristics, you need to select the proper rating of the machine. We can select the proper rating of the motor. Next, based on the motor requirement, capacity of the motor requirement, we can select proper rating of the power electronic model. How to select this power electronic model? Based on the motor requirement, based on the availability source, you need to select proper power electronic model. Suppose available motor is DC motor, then available source is DC source, then you can take chopper circuit here. Otherwise, source is AC, motor is DC motor, then you can take rectifier circuit, right? If power capacity is more, then you have to take 3-phase rectifier. If power capacity is less, you can go for single phase and enough, right? So based on the availability source, based on the availability of the motor, based on the requirement of the load, here suppose load requirement is 12 Newton meter. So let them that to change the position or to shift the luggage from one point to another point. Here let us assume that 12 Newton meter torque is required. So the motor torque should be greater than the load required torque, right? So load it required 12 Newton meter, but motor capacity should be more than 12 Newton meter. Like that, you need to select the motor. Otherwise, load capacity required power is 10 kilowatts. Motor capacity should be more than 10 kilowatts. With respect to power also, we can decide, right? So here, if motor capacity is 10 kilowatts, power electronic module capacity also you need to take more than 10 kilowatts. Next, one more important thing is this control unit. This is very, very important. Now we will try to put more concentration on this. Is now here we will try to put more concentration on control unit. By using this control unit here, first if you want, select the proper KP K values in control unit. Why proper KP and K values? If we select proper KP and K values, we can maintain always error 0. Error is 0 is nothing but actual response is exactly in phase with your command. Your command and actual response both are in phase, right? So in order to maintain this condition, here you need to select proper KPK values. As an electrical engineer, your job is selection of KPK values based on the customer requirement or based on the conditions. You need to maintain error always 0. So if you want to select proper KPK values, first step is you should have some mathematical characteristics, transfer characteristics of the load, transfer characteristics of the motor, transfer characteristics of the power electronic model, transfer characteristics of the feedback unit. All blocks transfer function you have to extract. Once you're having transfer function, later by using RH criteria we can find the KPK range, safe zone for the stable zone for the KPK values. Later we can decide. Once you know the KPK values range, later in practical condition, we by adjusting further, you need to adjust the KPK values to maintain error 0, right? So this is the overview of AC drives. In 1971, vector or field orientation control technique for AC motor is introduced. 1983, space vector PWM is introduced. 1986, direct arc. These all are control techniques, right? 1987, fuzzy logic is first applied to power electronics drives. 1991, artificial neural network is applied to motor drives. There are other control techniques also there. Here, compared to other control techniques, this one, direct arc control is very popular control techniques. Why it is very popular, later I will tell. So this is all the classification of induction motor speed control techniques, right? These control methods If you want, you can adapt for special drives also. If you want control the induction synchronous permanent magnet synchronous machine, next switch reluctance machine, where BLDC motor, you can apply any methods. Whatever control methods are there for induction machine, these methods are applicable for special machines also. Generally, here control methods are classified into two parts. One is scalar control, another one is vector control. Here scalar control nothing but in scalar control method, here we are going to control only amplitude of the voltage, amplitude of the currents, and amplitude of the frequency. There is no option to control the position control of the voltage, position control of the currents. We cannot control the position by using scalar control methods. But in case of vector control, we can control the amplitudes. At the same time, we can control the position of the currents, voltages. Also, we can control. These are the advantages. What is the advantage? If you are able to control the magnitude and position, we can improve the steady state performance. Sorry, we can improve the dynamic response of the system. That is main advantage. In case of here, the advantage of vector control is we can improve the dynamic response. But come to steady state, under steady state condition, scalar control method, even if you apply scalar control or vector control, under steady state condition, both control logics will give same response. But only in transient part, if you apply scalar control, transient response is more. It will take long time to reach the steady state here in practical condition. But if you apply vector control techniques, transient time it will reduce, acceleration time it will reduce, right? Nothing but dynamic response of the torque is very fast if you apply vector control. Again, in vector control, there are so many methods are there, like field orientation, feedback linearization, director control, passive based control techniques are there. Here out of these four, there field orientation and director control methods became very popular. Other methods, passive based control, feedback linearization, these methods are very complex, more parameter sensitivity. Implementation is also not simple compared to other methods. That's why these two methods are not become very popular. But director control method implementation is very simple, parameter sensitivity also less. That's why this method is become very popular, right? FOC is also very popular method for AC drives. Please try to understand here. Induction DC drives control methods are very simple. Here dynamic response of the DC drives are very fast. Reason is there is no nonlinear component. But in case of AC machines, because of nonlinear theta component, you have to apply these methods. By applying the vector control method, we can eliminate nonlinear component. Later I will explain how to eliminate nonlinear component. In next slides we'll try to discuss. So come to scalar control. Using scalar control, we can these are the classifications of the scalar control: voltage control, rotor resistance control method, EMF injected method, frequency control method, pole changing method, cascading of two induction machine. These topics are there in undergraduate program. Here in BTech level, we can, this all are speed control technique. By using scalar also we can control the speed, but problem is transient response is very poor, acceleration time is more. Why? Because by using these methods we cannot control the position, we can control only amplitude, voltage amplitude. By injecting the external resistance, we can change the torque peak point, we can shift the breakdown torque position, we can shift. By injecting the EMF, we can regulate the rotor current amplitude, such that we can change the speed also. Frequency control also, by changing frequency we can change the speed of the stator poles, we can control the speed of the stator poles. Once stator pole speed is controlled, at the same time rotor poles also will come closely to stator poles in such a way that we can control the speed, right? V by F also very popular method in scalar control. Next, pole changing, by changing the poles also we can control. Come to vector control. Here in vector control, by using vector control we can improve the dynamic response. There are two methods become very popular. One is field orientation technique, another one is direct arc control. Field orientation technique, here by using this technique we can eliminate the nonlinear component here. At the same time we can convert the AC machine characteristics similar to DC motor characteristics. We can reduce the AC motor torque expression order, torque equation order we can bring back to first order, right? So that is the advantage of the vector control, FOC. Direct arc control, also we can improve the dynamic response of the machine very fast, similar to DC machine, right? Implementation is very simple. These are all the drawbacks of the scalar control. Drawbacks is transient response is very poor, right? By vector, to overcome the drawbacks in scalar control, we'll go for vector. To satisfy the requirement of dynamic behavior of the drive, where fast response is required, then you have to take vector control. Excellent control technique to deal with transient. The only drawback of disadvantage of the vector control is it is very complex. Now first we'll try to discuss FOC, field orientation control. Here so in case of field orientation control, first step is first you have to extract this currents and here whatever you are taking feedback signal, that feedback signal you have to apply Clark transformation. So by applying Clark transformation, what is basically torque is in seventh order expression. Let us take induction machine for understanding purpose. Machine is motor is induction machine, control logic is FOC. Basically machine is in seventh order expression. So here by taking stator currents, by estimating the rotor currents, and by estimating the theta r, you will get torque expression in seventh order mathematically. So here by in case of FOC, step one is first you have to apply Clark transformation. By applying Clark transformation, Clark is nothing but three-phase to two-phase transformation. So by using transformation technique, same torque expression we can convert from seventh order to fourth order. So this is the torque expression in terms of in terms of two-phase circuit, right? So torque is depends on lambda dr IQS, lambda qr IQS. This is the torque expression after applying Clark transformation, right? So a second step is orientation. What is orientation? I will try to explain by using this phasor diagram. This is the mathematical phasor diagram of the rotor flux after applying Clark transformation. By applying the Clark transformation, the resultant rotor flux having two-phase component. Here, before applying the Clark transformation, the resultant rotor flux having inherently three components: rotor A phase, B phase, C phase, right? So rotor A phase, B phase, C phase flux we can transfer to two-phase component. Finally, what is the space displacement between two-phase component? 90 degrees. The space displacement between lambda dr and lambda qr is 90 degrees. But in case of before transferring from three-phase to two-phase to three-phase, three-phase to two-phase, in case of natural reference frame, what is the space displacement in rotor A phase, rotor B phase? 120 degrees. So by applying the Clark transformation, we can convert the resultant flux amplitude is same, location is also same. Only thing is the resultant flux realization is different in mathematic techniques. The resultant flux here we can realize by using these two components. One is lambda dr and lambda qr, right? D and Q are reference points. So this is the position of resultant rotor flux. So here finally here after applying Clark transformation, you will get this phasor diagram. Torque expression is in fourth order. So this is the advantage of Clark transformation. Next, one more advantage of the orientation. FOC, field orientation control technique. Second task is you have to transfer the reference point in phase with rotor flux axis. Understood? First task is you have to apply Clark transformation. If you apply Clark transformation, we can convert seventh order torque expression into fourth order torque expression. For fourth order torque expression, this is the phasor diagram. right? In this phasor diagram, D and Q are the reference points, right? Next, second step is you need to align orientation. So here, if you know the position of rotor flux, the resultant rotor flux position, nothing but theta E. If you know this theta E, this is the big task in field orientation technique. So by using so many techniques, there are other techniques, sensing technique or rotor flux sensing position techniques or estimation techniques. We can find this theta E. Theta E finding is very difficult in FOC. If you accurately sense the theta E value, then torque equation become fourth order to second order. That is the beauty of FOC method. In case of FOC method, main task is estimating theta E. So if you know theta E, where theta E is the position of the lambda r with respect to A axis, reference axis. This is the A phase axis, right? Let us assume that theta E is known value. Then after that, you need to transfer reference points with respect to theta E, right? Once you know theta E, D axis, let us assume that D axis is aligned. This D axis angle is also, if you are able to maintain theta E, D axis angle and theta R angle both are equal to theta E, then advantage is D axis will move in phase with lambda R. Once this D axis is aligned with lambda R, advantage is lambda QR becomes 0, right? If you take before applying the orientation, before transferring the D axis in phase with lambda R position, here torque is in fourth order. Once D axis reference point is shifted in phase with lambda R, then what is happening? Lambda QR becomes 0. If lambda QR is 0, then what is the advantage? Fourth order equation becomes second order. So mathematically the number of state variables are coming down. Basically, initially torque is having 7 state variables. After applying Clark transformation, then torque is in becomes fourth order equations. The torque is depends on 4 state variables. Next, after applying orientation, right, rotor flux orientation, nothing but reference point is shifted in phase with actual rotor flux, then torque becomes second order. So after obtaining secondary equation, then again you need to apply V by F method. What is the advantage of V by F method? By maintaining V by F ratio constant throughout the operation, then lambda dr becomes constant. If lambda dr is constant, then torque is depends on only IQS component, where IQS is nothing but torque control component, right? So by controlling only IQS component, we can control the torque. So finally, here for AC machine, by applying FOC technique, the resultant torque expression with respect to control circuit becomes first order. With respect to control circuit, what is the order of AC machine? Induction machine torque is in first order. So by adjusting only IQS value, we can improve the torque characteristics. So the characteristics of the AC machine, induction machine becomes exactly similar to DC machine. The dynamic response of the induction machine becomes similar to DC machine. By applying FOC technique to AC machines, we can improve the torque dynamic response similar to DC machine. This is the beauty of FOC method, right? Very simple. Only thing is it is more parameter sensitivity. Yeah, main big task in FOC is estimating of the rotor flux position is very difficult. That is a big task. Next, once you know the theta E value, next step is you need to transfer the D axis in phase with rotor position. Right? These are all the steps for FOC method. This is simple block diagram for FOC method. What are the drawbacks? These are all the drawbacks of FOC. It required reference frame transformation, it required Clark transformations, it required inverse Clark transformations. Control scheme is very complex. PA regulators, current regulators are required, PWM generators are required. FOC, it is more parameter sensitive. This is the one of the drawback of the FOC. Here to select DTC, before selecting DTC, here you have to think about parameter sensitive. In case of director, another method is director control method. FOC is very complex. By using FOC, we can improve the torque dynamics of the AC machine similar to DC. but problem is in real-time application implementation is very difficult, right? One more drawback is it is more parameter sensitive. Why? Because while estimating theta e, it requires a lot of equations means parameters only, internal parameters equations are there, more parameter. Come to direct arc control method. Direct arc control method main advantage is it is less parameter sensitivity, implementation is very simple. The dynamic response of the torque in direct arc control method is uh, higher than dynamic response is faster than the FOC method, right? Next, what are the challenges? What are the limitations of the inverter? Why inverter is required for AC drives or special drives? Special machines also without taking inverter here you will get, right? We cannot get starting torque, right? What are the limitations, significance and limitations of inverter? Without taking inverter, we cannot change the characteristics of the machine. If you want to change the machine characteristics based on the load requirement, here you have to take inverter. By taking inverter, you will get variable voltage and variable frequency component. By changing the voltage amplitudes and frequency amplitude, we can change the speed also. We can change the speed of the drive based on the requirement, right? But what is the drawback of limitation of inverter? Once inverter is fed to the machine, let us assume that this is the speed torque characteristics of the induction machine without any inverter. So torque characteristic is, this is the breakdown torque, this is called starting torque, this is the steady state torque. After applying the load, torque is matching, generated torque is matching with load torque. So here without any inverter, if induction machine is fed to pure sinusoidal sources, then torque response under steady state condition is very smooth. You forget about starting. Initially, if you take any drive, AC drives, it will take unbalanced currents, right? During starting accelerating mode, machine will take unbalanced current. Because of unbalanced current, torque will fluctuate, right? So what is the advantage of pure sinusoidal? Torque response is very smooth. Once induction motor is fed with inverter, see, both are average torque values are same. Both will give same average value. But drawback is instantaneous value. Instantaneous torque is fluctuating. Average, if you take average of this waveform, this average of the waveform is exactly similar to this value. But instantaneous value is very far from the average value. Fluctuations. This is called ripple. There are a lot of ripples are there in torque response once induction machine is fed to uh, inverter. This is the area. If you want to work here, there is a lot of research is going on this topic, reduction of torque ripple in the PMSM drive, induction machine, SRM. So generally the main sources for ripple is there are two reasons. One is because of mechanical structure, basic structure. Second reason is because of this control logic. By using control logic, we can reduce this ripple. Another technique is by changing the mechanical structure, by changing the fractional slot, by selecting the fractional slot machine, by changing the concentric winding, distributed winding, here mechanical side, machine designing side also, by taking precautions, we can reduce this ripple. Control side, by choosing different PWM technique, by choosing a different control technique also, we can reduce the ripple. There are so many papers are there on reduction of torque ripple. There is a lot of research is going on this topic. Yeah, these are all the limitations of inverter. Here now I'm having only 10 minutes time. If possible, I will try to complete this topic. Application point of view, I will try to complete within 10 minutes. So come to electric vehicles and hybrid vehicles. The main here, the main goal or advantage of the electric vehicle compared to IC based engines, main goal is reducing the CO2 emission. Next, operation is also very smooth. right? Next, one more advantage of the electrical drive is we can operate the drive in 4 coordinate operation: motoring mode, generating mode, forward motoring mode, forward braking, reverse motoring, reverse generating. This is the main feature. Compare, if you take IC engine, it will not operate. IC engine is always operating in one mode, mode one only. Here it will not operate. It cannot operate in generating mode. That is the problem, right? That is the main drawback of IC engine. So this is all the why we need electric vehicle. Second one is we can save cost. How to save the cost also, I will take one by taking one example. I will try to explain. Next, domestic energy independence, noise. Here if you take electric vehicle or hybrid electric vehicle compared to IC engine based vehicles, noise is very less. Vehicle, it will go very smooth, right? This is all the manufacturing companies in India. Electric vehicles, Mahindra. Full electric vehicles, Mahindra, Tata, uh, Tiger. Next, hybrid electric vehicles, Toyota, BMW, Honda, Maruti, right? These are all the companies, manufacturing companies in India. Pure electric vehicle and hybrid. Electric hybrid means combination of uh, electric and IC engine, right? So here, by taking this example, we can understand here what is the basic difference between electric vehicle, hybrid electric vehicle and uh, IC based electric vehicle. Sorry, IC based uh, vehicle. So case one, there are two cases are there. This is called IC based vehicle. Second one is motor is there, IC engine is there. This is called IC based hybrid electric vehicle. This is hybrid electric vehicle. This is IC based vehicle. So here let us have that with respect to shaft side, wheel side, it requirement is 4 kilowatts, right? To drive the wheel for a particular speed, let us assume that 4 kilowatt power is required. Here also, to drive the wheel for a specific speed, 4 kilowatt is the required power. So this is the gas. This is petrol tank. Let us assume that petrol tank. From the petrol tank, if you take IC engine, it will extract 41.7 kilowatt power, right? So if you take IC engine, the efficiency of the IC engine is only 24%, right? If you take 24%, let us that take calculation. 47 is the input. If you take efficiency 24%, then what is the output of the IC engine? It will give only 10 kilowatt mechanical power, right? This 10 kilowatt, again, what is happening because of auxiliary loads, because of uh, mechanical translation, because of these gates, again you have to consider 40%, 40% again efficiency, it will come down. Then 40% efficiency is going here. Remaining, how much you will get here? 60% only. The efficiency of the auxiliary load is, let us that only 40%. Then you will get 40 kilowatts 4 kilowatt power you will get with respect to wheel shaft. So this 4 kilowatt is sufficient to drive the wheels for a particular required speed. Next, if you take hybrid vehicle, to get 4 kilowatts, how much fuel it will take? Here, by taking this example, we can understand this. Let us that this is a petrol tank. So this is IC engine. So IC engine efficiency is 24% only. Here also 24, this one pure IC engine vehicle. This is the hybrid electric vehicle. Hybrid electric vehicle, nothing but IC engine plus electric motor, right? IC engine efficiency is always 24% only. Let us that if input to the IC engine is 24.5 kilowatts, then it will give 5.9 kilowatt power. Output mechanical power is 5.9 kilowatts. This output 5.9 kilowatt power is the input to the motor. Then the efficiency of the motor is generally 80 to 85, above 80 only. Then the output of the motor is 5 kilowatts. Compared to IC engine based vehicle, in case of hybrid vehicles, mechanical losses are less. Number of gears also less. Gear transmission system is less only. That's why auxiliary load efficiency, it will improve by 2 times. 8%, 80% efficiency you will get. So 5 into 0.8, then you will get 4 kilowatts. So what is the advantage of this hybrid electric vehicle? So compared to here, how much fuel is taking? 41.7 kilowatt fuel is taking. This is the amount of power extracting from the fuel tank. Here in case of hybrid electric vehicle, it is taking 24.5 kilowatt power only. Then what is the main advantage of the hybrid electric vehicle? We can save fuel, we can save cost, right? This is the mathematical by using this mathematical expression we can understand what is the significance of hybrid electric vehicle compared to IC engine based vehicle. IC engine based vehicle efficiency is very less, at the same time it is taking more fuel, right? But here hybrid electric vehicle, it will take very less fuel. At the same time, one more advantage is this motor in deaccelerating mode. This motor you can utilize for um, this motor, it will extract the power from the wheel, and it will generate the electric power. Whatever power is generating from the electric machine, you can further you can store in batteries also, uh, in, in such a way that you can improve the overall efficiency of the drive, right? So generally, hybrid electric vehicles are classified into three parts. One is series hybrid electric vehicles, parallel hybrid electric vehicles, series parallel hybrid electric vehicle. Hybrid electric vehicles, nowadays, many of the industries, they are concentrating on hybrid electric vehicles only. Pure electric vehicles production and come to application point of view, number of pure electric vehicles in practical applications are less. Reason is still there is lot of research is going on battery side. Still battery main challenge is battery charging and discharging, right? So in case of hybrid electric vehicles, you no need to charge the batteries, right? Simply you have to fill the fuel tank by petrol or diesel, that is sufficient, right? So series, based on the position of the motor and IC engine, we can classify the hybrid electric vehicles into three parts: series parallel hybrid vehicles. This is simple block diagram of the series hybrid electric vehicle powertrain. First, fuel tank is link is connected to the IC engine. Next, IC engine output is mechanical power you will get. From the mechanical power is fed to the generator, right? Generator output is converted to is connected to the power electronic module. Then by using power electronic module, we can change the voltage and frequency of the um to the motor. Then motor is connected to the wheel, right? So when our machine is operating in braking mode, whatever energy is stored in the wheels, here this motor it will extract, then it will fed back power to the converter, then power is stored in the battery system. This mechanism is required. In case of the advantage of series hybrid electric vehicle is power management is very simple. Energy management, right? Energy management and this block diagram control circuit is also very simple. Come to uh, parallel hybrid vehicle. In case of parallel hybrid vehicle, IC engine and motor both are parallelly connected to the shaft, right? So here when our machine is operating in motoring mode, during accelerating condition, what is happening? Uh, this path and this path both are in active condition. Once machine reach to steady state, right, only fuel supply, only IC engine is working. This part is discontinuous. This circuit is isolated from the coupler, right? Once machine is entering braking mode or deaccelerating mode, this path is disconnected or isolated from the star coupler. Then whatever energy stored in the wheel, it is fed back to the batteries bank, right? This is solar based. This is one of the option. You can place solar panel on the roof also. By using solar panel also, we can extract the power, we can charge the batteries also. This is one direction. And braking mode or regenerative braking mode, you can charge the batteries, right? So compared to series hybrid vehicle here, energy management is energy management or control the power is very difficult, a little bit complex, but resultant power capacity we can increase, reliability also we can increase. Whenever this IC engine fuel get completely discharged, also we can operate the electric vehicle through batteries also we can operate here. This is called series parallel. The difference between parallel hybrid vehicle and series parallel hybrid vehicle is this mechanical coupler. There is one mechanical coupler is there. Because of this mechanical coupler, then we can extract the mechanical power from the IC engine. That by using mechanical power we can rotate the generator, then you will get power. Here rectifier output is DC. By using this DC here, then we can charge the batteries. At the same time we can control the power, DC to AC we can convert, then control AC signals we can fed to the PMSN drive. We can change the speed, depends on the requirement. This is also compared to parallel, compared to series hybrid vehicle, energy management is very difficult, right? But reliability is more. For high power applications, more than 100 kilowatt applications, electric vehicles, they are using this type of mechanism. For low power application, less than 25, less than 20 kilowatt power application, generally series hybrid electric vehicle mechanism is very simple. Control is also very simple. For medium and high power application, generally they prefer parallel operation, right? Thank you very much.
Sir, on behalf of audience, there are some questions, sir.
Okay, you can.
Sir, first question is, what is the order of DFIG? Why not DFIG is used in case of wind turbines instead of PMSM?
What is the order of?
DFIG, double fed induction generator.
Order is 7, Praveen.
Order is 7. And why DFIG is preferable than PMSM? That is another question. Continuation.
No, PMSM cost is very expensive compared to double fed induction machine. PMSM is very expensive. There is here only this permanent magnet. Still, we are importing from China. Right?
Yes, the permanent magnets are not available in our country.
Not available. Next, one more is the number of suppliers are less. Demand is more in India. Permanent magnet demand is more, but number of suppliers are less. That's why cost it is cost. Suppose if you want to purchase 3 HP induction machine, right? You can less than 15,000 you will get, right? So if you want to purchase 3 HP permanent magnet synchronous machine, more than 1 lakh you have to spend, right? Once permanent magnet cost is coming down, then most of the double fed induction machines they will replace with PMSM only.
Okay.
Except cost, electrical characteristics of the PMSM is superior. Very good.
Sir, next question is, sir, briefly explain initial position estimation and how to estimate theta E in FOC.
There are a lot of methods are there to estimate the initial theta. Initially, let us assume that if you want know the position of rotor pole, first you have to unexcite the all windings stator side, right? Just you have to rotate the rotor by hand or any external force. You have to rotate. Then you will get back EMF on the connect voltage source, voltmeter or multimeter across the any one winding, right? Once multimeter is giving voltage, then we can sense the rotor position. That is simplest method.
Yes, sir. Using rotor position encoder and calculating theta R and theta SN.
We can easily. Next, in real-time application, generally nowadays most of the electric vehicle they are using DTC only. FOC, even in Vizag steel plant, In other steel companies, they are using direct torque control method for shifting the luggage also. For traction application, they are using direct torque control method only. Electric vehicle also, they are using direct torque control.
Another question, sir. Any reference book in this area? Some participant.
There are a lot of references are there. I will forward to my Praveen sir. Okay, later you can collect. Okay, so many good books are there. Pure electric vehicle, design of the electric vehicle, selection of electric drive for electric vehicles. There's so many good books are there. You can. I will forward to them. You later you can collect. Okay.
Okay. Sir, thank you for your valuable time and sharing very valuable information, sir. And this lecture has, in summary, in this lecture
Yes.
we have covered almost special machines and the electrical vehicle applications. There are many things covered in this session, so this will be very helpful to the audience. Thank you so much for your
Sir,
valuable time, sir.
sir, just a second. Can you suggest any book or reference for electric vehicle charging station?
Yeah, I will forward. I'm having 4 or 5 textbooks.
Okay, fine,
Right?
fine, sir.
I will forward to Praveen sir. Later you can collect. Soft
Yeah,
copy
fine,
if you
sir.
want, I will forward. Okay.
Okay, okay. Thank you so much, sir. Thank you so much.
Okay.
Thank you, sir.
Okay, Praveen.
Yes, okay, sir.
Thank you.
Thank you for your valuable patience, audience. Now, the another session will start in 5 minutes. So now time is almost 4:10 approximately. So you come back by 4:15. So today's last session will be taken by Venkataramanaiah. So he will take a lecture on multi-level converters, a literature review on multi-level converters, and then conclude. So come back by 4:15. So come back by 4:15. Thank you.
Hello, Mahesh sir.
Yes, please.
Mahesh sir.
Yeah,
Yes,
please.
good afternoon.
Yeah.
Yeah.
Good afternoon.
Mahesh sir, actually, I like the data is over. My data for mobile is over.
Okay.
So I am using my wife's mobile for the present, like for the attending this session.
Okay. Okay.
Uh,
No problem. No problem.
no problem, no? Okay, okay. Thank you so much.
Yeah, kindly mute your audio. Like when the session is going on.
Yeah, yeah.
Dr. Praveen?
Praveen sir.
Praveen sir? Is it there?
Sir, is it audible, sir?
No, yeah, your audio is audible.
Sir, slides? What
Slide.
about slides?
Yeah, visible. Else I log in.
For low voltage and high power applications. After the two decades, its applications have been extended to medium voltage and high power applications. So this is the topology for medium voltage and high power applications. And here you see, as the number of levels increases, along with the number of DC sources, number of individual semiconductor switches also increases. So to address the reduced count, reduce the switching count, Bhabhor introduced in 2007 another topology with a bidirectional switches. S1 is 4-quadrant switch and S2 also 4-quadrant switch. So he connected such a fashion without losing symmetrical nature. He introduced a new configuration where there is no H bridge. So there is no H bridge and only 4-quadrant switches you have. So number of switching devices for obtaining higher number of levels are very less. So I will give the mathematical expressions for the number of switching devices with respect to the DC sources and number of gate drive circuits in later slide. So recent times, this is the recent time topology. So here there are two parts. The author decided, instead of making like this or like this, he introduced one separate H bridge. Instead of having so many number of H bridges, only he introduced one H bridge, and he cascaded a positive level generator. Okay, so here at this point, with respect to this point, you can generate only positive polarity levels, and this H bridge helps to flip the output voltage in the negative side also. At the end, you can get a sinusoidal waveform at the load. Okay, so there are n number of symmetrical multi-level topologies are existed in the literature. For time being, I am showing some of the topologies which are very popular till 2006. Of course, still continuously number of reduced count topologies are presented in the literature. See here, this is NDC, number of DC sources in SMLI, and this
Dr.
is
Ramana,
sir.
can you just please click on hide button, like on the stop sharing behind there is an hide. Yes.
Yeah, thank you. Okay, so this is NDC, number of DC sources, and this is NL, number of levels at output, and these are the number of IGBT switches are used in the configuration, and this is IZ, number of gate driver circuits, and this is the output voltage you can get in terms of the number of levels. Okay, so if you see in this kind of topologies, some of the topologies may have IGBT driver circuits. IGBTs are, see here, 2 into n plus 3. If n is 3, that means if you have 3 DC sources, then you can get 3 plus 3, 6, 12 IGBT switches. But still you have number of gate driver circuits are less. It is only 8. Sorry, it is only 8. So in this case, you can assume that there are 4 quadrant switches which needs only 1 gate pulse to drive the 2 IGBT switches. So like this, some of the configurations are coming to the literature. And so what are the remarkable merits in symmetrical MLA? So modular nature. So you can easily replace, because all the topologies, all the modules have the same ratings, so you can easily replace. So modularized circuit layout have in SMLM. So it can extend it easily to higher levels. It can extend it to easy to higher levels. But the limitations are, it requires more number of gate driver circuits are required for the same number of levels, and large installation area and protection circuits are needed. Okay, of course, as the number of switches are increases, so generating pulses is very difficult. So higher control complexity have in SML. Later, another kind of family, asymmetrical multi-level inverter, where we addressed to reduce the number of DC sources for the same number of levels. So here, what they did, unequal magnitude of DC input supplies. See the first configuration here, it is so-called binary asymmetrical MLI, is introduced by Manjrekar in 1998. So here, the selection of DC sources in binary fashion, VDC, 2 VDC, and it is for n the order 2 to the power of n minus 1 VDC. So here, as compared with the symmetrical MLA, we are using very less number of switching devices for the same number of levels, as well as less number of DC sources. Later, there are few other configurations which is having a different types of DC values, DC source values. See, it is VDC, 2 VDC, 2 into 3 to the power of n minus 3 VDC. For nth order, it is nth order DC source, it is 2 into 3 to the power of n minus 2 VDC. So it is called quasi-linear multi-level inverter. And further, we introduced a trinary fashion where the DC sources are selected such a way that VDC, 3 VDC, and at the nth order DC source is 3 to the power of n minus 1 VDC. And there are hybrid configurations. So that means one H bridge and some configurations prior to the H bridge they arranged to get much more number of higher levels compared to the trinary, quasi-linear, and trinary, where we can get the ratios of the DC sources VDC, 2 VDC at the end, 5 to the power of n minus 1 VDC. So I will show you some other configurations as comparison here. See, here we have seen one more column. This is number of DC sources and number of levels, number of IGBT switches, and number of gate driver circuits. Of course, here you have seen one more, that is maximum number of switches connected in system. Okay, so when current path is there, so in each path, some number of switches has to be connected. All switches won't connect. So how many maximum number of switches are there in current path at any instant of time? So this you have to see, and this is the maximum number of levels as in like in symmetric SML line, and this is a selection of DC sources, how each author has chosen when they are designing their own topologies. But the problem with asymmetrical MLI is, of course, we have to see the merits, higher number of output levels with a given input DC sources as compared with the SMLI, and it is also extended to the higher number of levels. But so loss of modularity, because what we are seeing a different voltage ratings of the switches. So the modularity is difficult because different H bridges you are using with the different DC sources. So we have one limitation in asymmetrical MLA, that is loss of modularity. Of course, voltage unbalance also is there. So coming to the other kind of family is called hybrid multi-level inverter. So it's very interesting configuration. So the pursuit of synergetic approach, which combines the distinct semiconductor switches, topologies, and modulation strategies to optimize the power processing of overall system of the converter. See, in this configuration, it is a simple 7-level hybrid MLI with the distinct switches. So this topology is also introduced by the Manjrekar the same year. So what he did, he has taken, this is a 3-phase configuration, and he has taken 2 H bridges with the asymmetrical nature of the supplies. But if you see the switches, the top H bridge is used GTO or IGCT switches, which are block higher voltages. And coming to the bottom switches, here this is IGBT, and we can operate IGBT compared to GTO at higher switching frequencies. So this can operate at higher switching frequency, and it can block higher voltages. So finally, it can achieve a good harmonic profile at the output waveform for higher voltage applications. So that's what his intention. Then coming to this, another kind of hybrid MLI. So here, this is H bridge. So it consists of, actually, it is also 3-phase configuration. It consists of 2 types of inverters. One is standard for 3-phase inverter, that is H bridge. So 1, 2, 3. So for each phase we have 1 H bridge with the DC value VDC by 2. And another inverter is, so this is 3-phase H bridge, and another inverter is 3 individual H bridges. Okay, so what they did, they cascaded 1 full bridge and 1 half bridge to get higher number of levels instead of 2 individual H bridges. So it is very much suitable for broad range of voltage control applications like a traction drive applications. Okay, so later we can see another kind of family which are very popular recent days, this single DC source multi-level inverter, SDC MLI. So it is also comes under the cascade multi-level family, because we are cascading different, we might have cascaded H bridges or auxiliary parts like a transformers or capacitors to get the higher number of levels instead of taking more number of individual DC sources. Okay. So the most of the MLAs depended more input DC sources in SMLI. So thereby a large number of input transformers or rectifier circuits are required, but individual rectifier circuits or individual transformers, or if you are taking only one transformer, more number of tappings are required to having with the individual rectifier circuits to get number of DC sources. Okay, thus overall cost, installation area, and efficiency of the inverter are harshly affected at input side. Okay, so that's why. So we are going for the single DC based MLAs, and this is one type of configuration where we are using high frequency link transformer. So if you see this configuration in detail, this is DC to DC converter, it's open. And once you get the DC, it is square wave generator, that means it is also an inverter at high frequency. So this inverter operating at higher frequency, and this high frequency waveform is transferred from primary to the secondary side, and this secondary side tappings, we are having a rectifier circuits. These are the auxiliary circuits, auxiliary 1, auxiliary 2, depending upon the number of windings. It is 3n, but time being we can analyze like this. It is 3n, it is an n for one phase, and this is 3n and another phase B, and 3n n for the phase C. So these all auxiliary circuits are simple rectifier circuits. So uncontrolled rectifier circuits. At the end of this, output of this rectifier circuit or auxiliary circuit, you will have a capacitor. So to nullify the ripple, DC ripple. Okay. So these DC values, two DC values are connected to the off-bridge module. So we are using two modules, module 1 and module 2. So in this module, one auxiliary circuit is connected and another one is connected to like this. So we can treat these two off-bridge modules for one phase. These one, two are to the road for phase B, and this two is for phase C. So what he did, he simply used at the primary side or input side of the inverter a high frequency link. So nowadays we are calling HFL. So this is one kind of configuration where we are using a single DC. So it is very popular for PV systems. And coming to the other kind, so here this is cascaded transformer based MLI. So Phil Kung-song introduced this topology where he used a low frequency transformers. So low frequency transformers at secondary side. So similar kind of modules he has used. So see this portion, this is one, but his classification in the same topology is little bit different from the earlier topology. He used transformer so the output.
Your voice is not audible, Dr. Ramana.
Now, sir, is it audible?
Yeah, now it is audible.
Yeah. So in this topology, so transformer 1 will give only PWM output, and transformer 2, 3 will give a fundamental output voltage level, and we will cascade both. Finally, the resultant V0 will be the PWM output waveform. Instead of doing the PWM technique for all the switches, we are doing only some portion of the inverter, and remaining portion of the inverter avoided from the PWM. So like this, we can reduce switching losses as well as conduction losses of the overall topology. And there are another topologies, but I'm not introducing all the topologies here. But the problem here, see, there are plenty topologies are existed, but what topologies? Very few topologies are adopted by the industries. So and recent days, topologies, introduced topologies are trying to develop for the industrial applications. So that's why we have to see which topology is suitable for the which application. That is so very important. So here this slide says that so symmetrical topologies are not recommended for motor drive applications where we have a constant frequency output. Otherwise, you can see asymmetrical and hybrid and single DC topologies in the following reference papers. So it is very important to know about modulation techniques. So for controlling switching states and balancing of isolated input supplies or capacitors, sometimes we may use capacitor also. So we have to know which modulation technique is suitable for the application point of view as well as topology point of view. So we have so many modulation techniques and space vector modulation technique. So voltage level algorithm based techniques here, multi-carrier PWM, hybrid modulation techniques, and selective harmonic SHE, selective harmonic elimination techniques, and nearest level control technique. So here, especially multi-carrier PWM techniques further classified into two types. One is phase shifted modulation technique, where reference waveform is only one, but carriers are shifted with respect to the phase. And this is level shift PWM techniques. So it is further classified into three types. One is PD, phase disposition. So all carriers are positioned in the same way. And another kind is phase opposition disposition. So positive portion will have one phase and negative portion of the carriers are out of 180 degrees. And the last one is alternative phase opposition disposition technique. So here alternative carriers are out of 180 degrees. So choosing an appropriate switching strategy for a particular application and configuration is a challenging task because we have so many controlling techniques. So what we can see from the technical point of view, there is a still scope to further reducing in the device count from the existing topology. That's why still numerous topologies are coming to the literature. So, and moreover, so one topology might be evaluated with a particular technique. They may not have idea about other techniques. So we have to see each topology with a different controlling techniques to see their efficiency in all perspectives. So let me introduce one small topology in detail. See, this is a 19 level configuration. This comes under the hybrid configuration. See, with a very less number of switching devices, we have generated a 19 level. So this is one H bridge. It's like Philkungsang. They are using only two transformers. Philkungsang introduced three transformers for only 5 levels. If you take the same configuration, then here you see the DC sources. So V1, V2 are in the ratio of 1:2, and so it is not too much difference. So 1:2, and this bridge B is operating at PWM, and bridge A is operating at fundamental, and the transformer ratios also 1:1 and 1:2. So I will explain about switching states of positive 19 level voltage waveform, because negative level is just replica of that. So here for positive level SEA1, SEA2, these two will turn on. For the negative level, these cross switches will turn on. That is the only difference. So that's why I'm explaining only these 9 levels, positive 9 levels. Here, if you see one H bridge, and in H bridge, bridge B also we have another H bridge. So the complete operation to generate this part. Okay. So positive, we have to turn this one, and we have to start this two, any lower or upper. So when you turn on SB1 and when you turn on SB6 and SB1 and SB2, so these SB1 and SB2 bar will give positive level, and then these two will make to operate V1. So SB3 will go SB1 and will reach the primary winding of the transformer, SB2 bar, and it will return to the SB6 for the V1. For V2, both switches will, only SB5 it will turn off, SB5 will come into the picture, then source V2 will come into the action, and it will feed the supply to the load through SB5. For the all positive levels, SB1 and SB2 bar will turn on. So it will come through SB4. And for 3 level, we have to operate only SB3 and SB4 with SB1, SB2 bar. So remaining switching states are here. So followed by these switching states, remaining switching states also we can see. Now, so this is complete output waveform for each bridge. So this is bridge A, it will give a quasi-square waveform, and it is in per unit values. and this is bridge B. It is PWM waveform. Okay, when you combine both at secondary sides of the transformer, then you will get a 19 level output waveform. It is PWM. So here you should not forget that, see, these primary side windings are still have the voltage levels of V1 plus V2 as the maximum, but secondaries are not the maximum of these values. See, both are combined, then the voltage level, maximum voltage level is too high compared to the primary. So switching stresses, voltage stresses on the devices is less compared to the other kind of topologies where doesn't have transformers at the secondaries or nearer to the load. Okay, so that is a one benefit of the transformers when we have at nearer to the load or after the H bridge, after the inverter. So that's what here also I mentioned. You can, so this circuit can be extended for the n number of levels in two possible ways. So by appending additional DC sources in H bridge B, right, bridge B symmetrically or in asymmetrically fashion also. So this is the way you can get number of levels when compared to the, when related to the number of DC sources. Similarly, in asymmetrical fashion also, you can design the same converter for high power applications. Now we'll see a switching technique for this topology. See, the switching technique, a new switching technique I want to explain now. So we all know about PD, POD and APOD. I want to introduce a new switching technique in level shifted pulse width modulation technique. Okay, LSPWM. Here, what we do, according to the phase position of the carrier, LSPWM technique are classified into three types, as I said earlier. Among these three, POD is an audacious competitor than the other two approaches compared to, as he said. So I adopted POD, and what we did, a carrier frequency is usually keeps high to curtail the lower order harmonics. That's what we do in POD techniques or APOD techniques for the multi-level inverters. Because if your carrier frequency is too high, because we are operating multi-level inverters for high voltage applications, dV by dt is too high. Am I right? So when we are reducing the carrier frequency as low as possible, then we can reduce the dV by dt ratings. Okay, so stresses also will come down, switching losses also will come down. So as switching frequency increases, switching losses will be high. So that's why we need to operate at lower level in multi-level. So that's what here we can see, switching and EMI issues are very severely affected the operation and control of the converter. So what we do, a new carrier is proposed for supersedes the traditional carriers. So we are concentrating on the only traditional carrier which can reduce the switching and EMI issues. Now, so this is a new carrier. So I will explain in detail about this carrier in further slides. So that's what, as I said earlier. So we are considering a new type of carrier which can reduce switching losses as well as EMI issues. It is originated from the POD techniques, that means level shifted techniques. So we need same new carrier also for n levels. We need NL minus 1 carriers as like POD or PD techniques. So it is POD technique. That's why all negative carriers are 180 degrees apart with the positive carriers. Now we will see a new carrier. Why we have to concentrate on the new carrier? See, this is output waveform, instantaneous output voltage waveform equation Fourier series. So if you see, this component is average component, it should be 0 in general, and this component is contributed a reference waveform, and these two components are contributed by the carrier waveform. So the carrier waveform also decides the harmonic quantity in the output voltage waveform. That's why we have to concentrate not only in the reference waveform, carrier waveform also. Okay, so I will skip this one. We'll go to a carrier waveform generation. So it is a simple triangular waveform. We might have used sawtooth waveform also. For time being, I am taking the consideration for the triangular waveform. So this is a triangular waveform at higher frequency. It might be 1 kHz or 2 kHz in multi-level inverter perspective. So what I did, I have split it equally into 6 parts of the same carrier. Okay, 6 parts, and time interval is T by 6. This is the time interval T by 6. And this line 0.85, 8.5 magnitude line is my reference waveform. Okay, my reference waveform at some portion, because carrier frequency is too high. So I am considering this is more or less a DC value, Then what I did, I already split it into 6 equal parts. Okay, so these intervals are decided. So carrier is 1, 2, 3, 4, 5, 6. Carrier have 6 points with the interval of equal interval Ts by 6. So interval 1, so if you leave the 0 interval, this is interval 1, and interval 2 are the points D1 and D2. Okay, D2 line may cuts interval 2 and 4 also. D1 line may cuts interval 1 and 5 also. Okay, so now at this point I am taking a difference delta. So delta is D1 by minus D2. So for this waveform, for the presenting waveform, delta is negative because D1 minus D2. D2 is higher magnitude, so delta must and should be a negative value. So for pure triangular waveform, it will be minus delta. Difference will be minus delta. Now, when I am pushing this button, this D2 button or D1 in, at the same time, I will push this up and I will push down this. So after some time, I will changing the position of D2 and D1 such a way that delta magnitude will come down, or you can say negatively it is reduced. So earlier it might be 0.3, now it will be minus 0.1. It is minus 0.3, now it is minus 0.1. Now here also, so and moreover the pulse width also come down. Am I right? So here also, now the position of delta become, the value of the delta become positive because D1 is positive and D2 is negative. So like this, when this D1 and D2 reaches the position like this, then it will be a triangular waveform with the frequency triple compared to the first case. Okay, so like this, when I move the positions of the D1 and D2, then I can attain at this point. So when we perform the analysis of the inverter with this kind of the carrier waveforms, we interestingly observe the result with this kind of carrier waveform in terms of the THD as well as higher order harmonic position. Now we'll see here the value specified that delta is minus 0.3 for the case A, and delta is minus 0.15 for case B, and delta is plus 0.45 for case C, and delta is 1. So when delta is 1, that triangular waveform with the 3 times of the fundamental carrier frequency. So for this, what we did, I will take this carrier waveform where delta is plus 0.45, then this is the results I have seen from the configuration. See, at delta is 0.4, we can see the variation of the delta. So at delta is 0.45, the THD value for the 19 level is 5.29, and peak value is of course more or less same in all the cases, but the interesting result is here. Okay, interesting result is here. So the dominant harmonic is shifted from 61 to 59. Why it is 621? Why it is 2190? Because it is POD technique. So we have considered 1 kilohertz. So MF value is 20. So it will be plus or minus 20, plus or minus 1 of 20. So 21 and 19. But with the same carrier, by changing the delta value, what I did, I have attained a different dominant harmonic values. So this is 61 and 59. So at this juncture, we can use a less filter size with the same carrier waveform. So the DC values, as I said earlier, it is like this. So 1:2 ratios. Now, this is the way we can implement this new carrier waveform. And this is deadband circuit is mandatory for complementary switches perspective. So deadband circuit we have to use, and when we are giving the pulses to the bridge A controller and bridge B controller, then you can implement this complete switching scheme for attaining the 19 level PWM output waveform. So how can we decide whether switching losses are reduced or not? So there are two ways of calculating the switching losses as well as conduction losses. So in practically we have to consider the data sheet details of the any switch what we are using in the configuration. So if you are using SKM 75GB 123D switch, based on the data sheet, you have to calculate conduction losses as well as switching losses. So these are the equations. So we have a switch IGBT. Sorry, here it is a IGBT and anti-parallel diode. So we should have equations for all 4 semiconductor devices. This is IGBT power losses conduction loss equation, and this is at higher temperature. So maximum temperature 125 degrees. IGBT power loss equation. Likewise, diode for the different 2 extreme temperature equations. So these equations are attained by using a practical data sheet, and we have used a curve fitting approach. So in the curve fit approach, as where we are using the current level in the topology, according to that curve level, we can fit in the curve for attaining the equation. So you can go for the polynomial, different kind of polynomial if it curve is not fitting properly according to your details. So there may be the temperature dependency in the switch. So that's why we have to incorporate temperature coefficients in the equation, same equation. So here we have incorporated the temperature. This is the temperature, T variable. As T changes, so losses of IGBT as well as diode also will changes. So this is the operating current IC in the IGBT. This is the forward current, operating current in the diode. So these two are the parameters which affects the losses in switches. So coming to the switching losses. So this is the switching losses of the semiconductor devices. So this is a simple schematic diagram of any switch in MATLAB. You can implement this in MATLAB. So what we did, this is the gate pulse, and you have to detect the pulses where it is rising or where it is falling. So once you calculated the transitions, you have to use unit delay. This is we should not forget this unit delay, because once it recognized, it won't give the exact position of the up or down transition. It will take one step of the MATLAB programming. So that step we have to take it back. So forgetting the exact instant of switching transition. So this unit delay we should not forget. And finally, this is a composition of the equation. So here also the variables are collector current, and where the instant at the switching instance we have to multiply with this E total, energy loss at both rising and falling. That means turn on time and turn off time. So both you have to calculate per a second, and meanwhile for getting the mean you will get a total losses of particular switch. Likewise, you should have so many PSL outputs for corresponding to the individual switches. So when we do the simulation for the same configuration, bridge A output voltage is like this, and bridge B output voltage like this. If you see here, it is like a PWM output waveform. It is a quasi-square waveform, and these figures for having the parameters, simulation parameters of modulation index 1 and delta is 0.45. So we can do the complete delta values for the same configuration, but we already discussed that 0.45 is efficient one. That's why we assume 0.45 for the further analysis. And carrier frequency is very less. So normally most of the real-time simulators for multi-level inverters, we cannot go for more than 3 kHz or 4 kHz. So if you are come down, then it will be more beneficial for the larger circuits in the real-time simulators. And these are the ratios. So transformer A and transformer B ratings also are given. This both transformers have the line frequency operating transformers. Now when both are matched or both are added at the secondary sides of the transformers, so once you cascade it, you will get the 19 level output waveform. So as modulation index come down, the number of levels also will come down. Okay, the overall THD of the simulation, you will get 5.81. See, here the dominated harmonic value is more or less 61 and 59. So that's why it is not giving more than 50 in simulation. So if you go to check the other harmonic order, then you can find as at 61 and 59, you can see the maximum magnitude of the harmonic. These are the experimental results for different modulation values. See here, when modulation index is reduces, then the number of levels at output you can see. This is pink color is 3 level output voltage at modulation index is 0.05. So as modulation index is varies, the number of levels are increases. See, it is a 7 level. Till at this point, we should not forget, till 7 level, bridge B can give the voltage levels. So beyond the 7 level, we have to depend on bridge A. So after 7 level, see here at 0.57, this quasi-square waveform, when it is added to the uneven waveform, you will get a 13 level output waveform. Okay, this is a 17 level output waveform, and the width of the square waveform, quasi-square waveform, will increases as number of levels are going high. Now, so this is at modulation index 1. You can see this one is operating at higher modulation index. So this one is 19 level waveform, and the load is RL load. So if you can see this one, load current is a little bit shifted from this point. Okay, so this delay is because of load is RL load. And see the practical load current and load voltages. So the load voltage THD is more or less lesser than 5%. So most of the cases less than 5% THD is acceptable. So when you compare this topology with other topologies, we can compare so many topologies, but for the same kind of family we have to compare. We should not compare with the capacitor based configurations. We have to compare with single DC source based configurations with transformers. Okay, so here if you see 19 levels by using only 2 DC sources as well as 12 number of semiconductor devices. The number of transformers also 2 as compared to the Phil-Kung-Sang configuration. So these are the parameters for the experimental verification we consider. Now, so in this configuration, what you can observe is that a single phase hybrid multi-level inverter which employed low frequency transformers for boosting the output voltage levels. So most of the cases, we have 2 options to boost the levels. One is capacitor, another one is transformer. If you connect the transformer at the secondary side of the output of the inverter, you can get more number of levels as well as primary side also. But when you are using the transformer primary side, it should be high frequency transformer. Another kind of families is by using the capacitors, you can increase the number of levels of the topology. So in this topology, we are used the light frequency transformers to boost up the voltage levels. So we are able to see how the variation of the carrier, modification of the carrier affected the FFT spectrum of the ML. So it has only 2 bridges, not more than that. So it is very suitable for the grid connected applications. We have to evaluate this topology for the grid connected practical issues. So we will do that. And this is the another kind of topology. Topology is same, but what we have to do is it is operating at fundamental switching technique. So there are 3 types of fundamental switching technique. I cannot specify the number. There are more number, but traditionally we are able to see 2. One is selective harmonic elimination technique. Another one is nearest level control technique for multi-level inverters. So when you are operating the converter with selective harmonic or nearest level control technique, we have to see the switching instance. So as I said earlier, topology, it is similar to the earlier topology, but we small modification here. So here you can see modes of operation in detail for each and every level. Okay, so this is the 0th level. So for the 0th level, all upper switches of the H bridge, here upper switches of the H bridges are short connected, and for the 1E, you can operate only one. This is the H bridge, bridge B, and this is bridge A. Okay, this portion have to operate till 3. Till 3 or this side. So this side is giving only 0 voltage. Okay, so like this, all modes of operation of the topology is given. So I am skipping this one. Now we'll see. We know fundamental switching techniques, as I said earlier, SHE and nearest level control. So compared to these 2, we can see these are some difficulties. I will explain what are the difficulties in further slides. But I will introduce a new controlling technique, so-called fundamental side quantization switching technique. This is very easy to understand, okay, as well as implementation also. What we will do, so we will take the reference waveform and we will quantize it, and this is the quantized waveform, and we will compare this quantized waveform with the earlier sine waveform. We will get the instance and we will correct that and we will give to the switches. That is very simple. Simply we have to quantize it, we have to compare it and get the VGC, get control signals and fed to the switches. So this is very simple technique compared to the sine SHE as well as nearest level control technique. I will explain a brief about this technique. See, this is a mathematics also, we can see very simple mathematics. This is V reference formula, V peak value into sine 2 pi 50t. So what we will do, so quantizing this output waveform, so this is the quantized output waveform notation VQ. So what we will do in quantizer, we have to see the equal magnitude, so quantization interval Q. So quantization interval Q we have to select in the quantizer. So this will be depending upon the VP. So VP and 0.5 into m minus 1, where m is number of levels. So here we have 19 level, that's why it is 18. So 18 into 0.5 will be 9. Okay, so VP by 9 is the Q value. VP by 9 is the Q value. So it is evident that, this is a very important note, it is evident that peak magnitude of V reference signal and quantized waveform should be the same. So you should not take another reference waveform here. You have to take same reference waveform to quantize the output. Okay, so you can vary the different Q values. So this is 1. At maximum you can get 1 VP by 9. VP by 9. So we can reduce the Q values also, but you cannot reduce VP by 9 further. So it should be VP by 9 only. It should not be VP by 10. That's what the meaning it is. See, what will happen here? See, these are the switching instance when you are comparing. This is reference waveform and this one is stepped waveform is quantized waveform. what you are doing, you are comparing this stepped waveform with a sine waveform. Then these are the instants. These are the instants alpha 1, alpha 2, alpha 3, alpha 4 are the instants where stepped waveform are raising from one level to another level. Okay, so from this waveform, what I want to explain is how we are extracting the switching instants, these angles. Okay, so E is magnitude difference between the consequent levels of quantizer output waveform, and alpha ith switching angle, where the waveform jumps from I minus 1 level to ith level, and VLN is RMS inverter output voltage, and M is the number of output levels. So consider one instant at this point. So here if you see, so at alpha 7, see at this point, okay, so this one is 7E level and this one is 6E level. So obviously it will be in equal area criterion, it will be 6.5E. Okay, so 6.5E at alpha 7, this value is 6.5E. Now, so this point of quantized waveform is 6.5E. And what about sine waveform? That means reference waveform. So reference waveform magnitude is Vp into sine alpha 7. Am I right? So alpha 7 we know. So Vp sine alpha 7 is this value, this instant value of the reference waveform. So when you equate both, then you can attain this value. So you can attain this value. Like this, you can get, when you substitute 3 equation into 2, then you can get alpha 7. Similarly, for I levels, alpha I, so sine inverse of 2a minus 1 by m minus 1, where I is 1 to 2 till m minus 1 by 2. Like this, you can simply get alpha I values. So see, once you get the alpha I values, so this is RMS value of the output voltage waveform. So this is for 2 level, I am taking consideration for 2 level for understanding the switching technique. So what we do, we have a PWM output waveform, the uniform PWM output waveform, I can say. If it is uniform, in FSQW you cannot get uniform. It is even though figure is showing uniform, it is not uniform. Okay, so alpha 1, alpha 2, alpha 3, these are the number of levels before pi by 2, alpha m minus 1 by 2. You can get this number of angles. So once you get these angles, you can directly give to the switches, then switches will operate according to the source. You will get the output voltage waveform. So this can be applicable for the three-phase systems also, where we have to consider the VP value is line to line voltage peak value, not a phase voltage peak value. Okay, VP value is Q depends on only line to line voltage values. Okay, these are the different Q values for the same topology. For present topology, you can get at maximum Q value is 1 by 9. You cannot get more than that. That's why I am getting 1 by 9. Okay, so this value 1, 1 by 2, 1 by 3. When Q is 1, you have a 3 level. When Q is 1 by 2, you have a 5 level. Like this, when Q is 1 by 3, you can get 7 level. Similarly, when Q is 1 by 9, you can get 19 level. So these are the simulation switching angles, and these are the theoretical switching angles, and the error is very less. It's not more than 0.5. So when you simulate, this is experimental also with the same values, and you are not nullifying the all ordered harmonics, but you are reducing the magnitudes of the lower order harmonics. So overall THD you have to see. The limitation of this technique is you cannot apply this technique lesser than the 15 level topology, because if you have these magnitudes, lower order harmonic magnitudes, as it's a little bit high. So when you are go for more than 15 levels, so overall THD, if you see, so these are all by varying the Q value, different number of levels. Let me skip this one. Yeah. So see overall THD is very less. So when Q is 1 by 3. Okay. So these are all individual harmonics. Overall THD is not more than even 0.4%. Sorry, 4%. Okay. So So comparison I need not to explain. I want to skip this one. Is similar to that, but only diodes are changes. So when you see this one, selective harmonic elimination technique as well as nearest level control technique compared with the FSQ, see it is very easy to implement. Okay, but it is not for the lower levels. That is the limitation of this one. Okay, that is the only limitation. And compared to other, we know as the number of levels increases, so initial guess is very difficult in nodal absorption method. Okay, so of course we have so many optimization techniques. Still, it is giving a good THD profile. And these are the final results we can get from the both techniques as well as topologies. At this juncture, I want to conclude. Thank you. Any doubts?
Ramana sir, thank you so much for your valuable time and your lecture on multi-level emitters, literature review, and some modulation techniques. So there are some questions from audience, so I will go through them.
Yeah.
Questions, sir. First one, how to generate alternate carrier signal in Simulink? Can you tell me the logic, sir?
Sorry?
How to generate alternate carrier signal in Simulink?
Alternate carrier signal.
Somewhere
Say alternate carrier signal. Question itself is little bit
alternate, not alternative.
means
see, we can simply give a 180 degrees phase shift for the previous signal. That means original signal, if you give the 180 degrees phase shift by selecting the each point, if you are selecting a triangular waveform, if you have to see the instance of the triangular waveform, then you can flip the positive magnitude to the negative magnitude. Instead of giving positive one, if you give the negative one, you can generate the alternative signal, alternative carrier signal.
And those are there are other questions. Can you suggest best 3-level RSC MLI as compared to conventional NPC inverter? And how to choose particular value of switching frequency of an inverter?
Switching frequency, you have to think about, if it is a lower level inverter, you can go for more than 9 or 8 kilohertz, because according to the application, for lower level inverter, you can go more number of the higher frequency level. Okay. So, yeah.
It is preferable to use high switching frequency. For high switching, we should go with low switching frequencies. So based upon the application, we have to select switching frequency of the inverter.
Yes.
Next question, sir. What is the logic behind having carrier waveform for multi-level inverter controller used in the slides? So
yeah, that's what. So when you see the Fourier analysis of the output waveform of multi-level inverter, so carrier also plays a major role. So appropriate carrier selection is also very important for analyzing the output waveform. That's what the mathematical equation what I have shown.
So last question is, can we implement SVPWM for the proposed strategy? And what is the difference between POD and APOD? Means phase opposing disposition and asymmetrical phase opposing disposition.
Yeah, obviously we can apply same technique, that means POD as well as APOD, but so both are almost mirror to the same, only the position of the carrier is a little bit different. So in POD all the carriers are same, but in POD little bit difference. But what you can see in performance analysis, in PD the dominant harmonic will be MF, so frequency modulation index. But in POD, phase opposition disposition technique, dominant harmonic will be the double 2MF minus 1. So most of the cases POD is more optimal solution. So because we are reducing the filter size of the inverter, because the dominant harmonic is shifted to the 2 times of the MF modulation index.
So last question from the audience, Saeed Alam, he has written how to decide initial values of switching angles in multi-level inverters.
Initial angles, the initial angle problem is only difficult in selective harmonic elimination technique, where we want to specifically eliminate the one harmonic. That's why we need a initial guess. So it is a little bit tough. Otherwise, you can choose. If you are not worrying about the lower order harmonics, you can choose the different angles, but it is not a good way, because lower harmonics always need to be low values or it need to be nullified.
Okay, thank you, sir. Thank you for your valuable time and spending, and thank you for your
Thank
listening
you.
and
Thank you,
addressing the
Praveen.
questions from the audience. So, when now today's session almost finished. So tomorrow the session will start at 10 o'clock, and
No,
many of
9:45.
9:45.
9:45. So many of
9:40 will.
asking for the net. So net we cannot do anything. So you have to adjust your plan accordingly. Feedback link will also send tomorrow only. So today sir is preparing. So tomorrow you have to fill up the two forms, today's and tomorrow's both. So tomorrow you should come back by 9:45. Thank you. Thank you. This is the end of today's session.